Hi everyone, my name is David Goodman. I'm a student here at the University of Michigan. This summer, I was a member of the SHARE program and worked under Professor Sarah A. Posey in the Detection for Nuclear Nonproliferation group. I worked on a dual particle imager for the detection and localization of nuclear materials. Let me show you around. Wait, did you really think I'd take you to the lab right away? Before we do anything in this group, we run simulations on our computing clusters. We use the radiation transport software MCMPX Bellini to test different detector setups and geometries. If you take 15 minutes here, you can save yourself an hour and a half in the lab. Now that we've taken the time to plan things out and we've badged up, we're ready to go into the lab and do some real work. Now our system uses radiation detectors called scintillators. These create analog waveforms that our computer can't read. Luckily, we have a way around this. Our computer takes the analog pulses from our detectors that are shaped by our pulse shaper and that are finally digitized into the language that our computer can read. Now when you look at our reader right here, we're getting some pulses. How does this happen since we don't have a source out? Well, you may not know this, but you're always surrounded by radiation in your everyday life. And characterization of this radiation is very important for aiding in the assay of special nuclear material in field. And now, for the nitty-gritty of how our dual particle imager works. To determine the incident angle of photons upon our system, they must interact in one of our scatter planes, which are liquid scintillators, and be fully absorbed by our sodium iodide absorption plane. Neutrons, on the other hand, must scatter in each of the scatter planes to determine their incident angle. You may ask how our scatter plane can discriminate between photons and neutrons when they're traveling so quickly. Well, we do this by comparing the total integral of the pulses created in our detectors to the integral of their tails. Neutrons deposit their energy more slowly than photons, which yields a larger tail integral. By using this technique called pulse-shape discrimination, we can effectively tell what an incident particle is. We use sodium iodides in our absorption plane because they allow for full absorption of gamma rays, yielding what is called a photopeak. When you add this photopeak to the energy deposited in the scatter plane, you can reconstruct a particle's total energy. In the end, we determine thousands of incident angles of particles, which are back projected onto a sphere, which yield cones. These cones overlap through the statistics, where the source is most likely, yielding hotspots, as seen above. You can determine where a source is by eye using the back projection image, or you can use MLEM, which is an iterative algorithm that compares predetermined system responses against measurements that aids in determining where a source is. Now that we have seen the basics of how our system works, we can better understand my specific contributions. I implemented propagation of uncertainty into our system. Due to the limitations of real-life measurements, there is always some error, which leads to degradation of measurements. Quantization of this error leads to more accurate back projection images as we focus on good events. I also created a visualization script to help illustrate particle paths within our system. In such an abstract field as nuclear engineering, concrete images and examples always help expand understanding of what happens in real life, leading to future innovation. Now with that said, let's get on to our system capabilities. Since we have a dual particle imager, we can detect both photons and neutrons. When a source is unshielded, both neutrons and photons reconstruct well, and when added together, produce an even better back projection image. However, when a source is shielded with a high Z material such as lead, photons are stopped. This is why a doctor gives you a lead vest before taking your X-ray to protect you. Neutrons, however, are unaffected by this type of shielding, yielding a good image. However, when we shield our source with plastic, neutrons are stopped, while photons are unshielded. When you combine both types of particles, you can still get a good back projection image. When both types of shielding are present, not many source particles escape. However, by detecting both neutrons and photons, we get better statistics than by looking at one type of particle alone. These better statistics yield a finer back projection image, which is useful for accurately determining where a source is. This means that our dual particle imaging system has many security applications where locating a source is very difficult because it may be shielded by metal and plastic, such as in a container ship. I'd like to thank my group and Professor Posey for letting me study alongside them this summer. I've learned a lot, and I'll be sure to carry on this knowledge into the future. Go Blue!